Consider this is a beaker of water and you are going to drop two things in the water. One is a wood and other is a small iron nail. It is your daily life experience that this iron nail always sinks to the bottom and this wood always floats on water. Whatever may be the mass, this will happen always. This is not because mass of these two things. If you consider 2 kg of wooden black, it will definitely float on water. And if you consider 5 grams of iron nail, it will definitely sink to the bottom of water. So, some other quantity should be defined. This iron nail is sinking, and why this wooden black or thermocol is floating. And that quantity is density, which is nothing but mass per volume. In other words, we can say the mass presenting in unit volume. Units of this is mass is measured in kg in SI system and volume is meter cube or cubic meter, and in CGS system it is gram per centimeter cube. Why this nail is sinking? Why this wooden black is floating? Means the density of wood is always less than density of water. Density of this iron nail, iron is greater than density of water. If two substances are given, they don't have known volume. In this case, we have to find out the relative density, the comparison of density of object with density of water. This is the experiment to find out the relative density of materials, and these are the materials required for this overflow jar or overflow beaker, which is like this, and empty beaker should be taken. This is empty beaker and electronic weighing machine to weigh the objects and to weigh the displaced water, and water is essential thing here, and objects like marble, wooden cork, eraser, plastic cubes, and etc. Whatever you have, and one thing should be noted that these objects should not be hollow. And here the procedure: overflow jar should be filled up to the beak. Beak means this is called beak, and overflow jar should be filled up to the beak, and any object is dropped into the water. The displaced water should move from here and collected in this jar. And weight of the empty jar. This is empty jar, and weight of this jar should be calculated or measured with the electronic weighing machine, and the weight is noted. And weight of the displaced water. After dropping the object, the water will be displaced, and we have to find out the weight of displaced water. This weight of displaced water is calculated from this formula: weight of the displaced water plus the beaker minus weight of the beaker. This is the formula should be used to find out the weight of displaced water. We have to use a pin to immerse objects into water. Objects like plastic cubes, eraser, these are the objects which will not sink into water, and we are unable to immerse these materials without using pin. That's why a pin should be taken, and we have to push the object using pin into the water. And this is tabular form, and we have to note down the readings for every object, each and every object. For example, if you take marble, and we have to weigh the marble weight with the electronic weighing machine, and here it should be noted, and that marble should be dropped into the water. Care should be taken when the object is dropped, the water should not be splashed out, and when the object is say marble, when the object is dropped here, the water will be displaced. Whatever may be the volume of the marble, equal volume of water is displaced from this overflow jar, and you have an opening here, and that water is collected in this empty jar, and that displaced water, weight of the displaced water should be noted here, and finally relative density is to be written here, and this is the formula to find out the relative density of an object. Relative density of an object is, this is the comparison of density with water. So this is density of object by density of water. As the volume is unknown, here we are doing that the volume are made equal, means the volume of the object and volume of water are made equal. We already found the weight of the marble and the weight of the displaced water. These two are having equal volume. The displaced water is of equal volume of the object taken. So this volume are equal. So finally this equation becomes relative density of object is equals to mass of object by mass of water. So we can consider relative density of an object is weight of the object by weight of the displaced water. Why we are considering weight means weight is nothing but mass into acceleration due to gravity. Here the acceleration due to gravity is constant here, the mass is replaced with weight. So relative density of the object is weight of the object by weight of the displaced water. If you get the relative density as more than 1, then that object sinks in the water. If that relative density is less than 1, then the object will float on the water. Repeat the experiment for some more objects like cork, eraser, plastic cubes, and etc., so that you can find relative densities of different materials. Relative density of a liquid. To calculate the relative density of a liquid, we have to find out weight of a fixed volume of liquid whose relative density is to be calculated, and weight of equal volume of water. Means the volumes of liquid and water should be same, and we have to find out weight of this liquid and weight of the water, and this is the formula to find out the relative density of a liquid, which is weight of the liquid and weight of the water of same value. These are the some values of relative densities of different materials. Here some solids are given and some liquids are given. The reference is water here. Lesser density than water means the relative density value is less than 1, then it will float on water. For example, wood, which is having 0.2, floats on water. Rubber, wax, oil, kerosene, petrol, these will float on water, and the relative density of few materials are more than 1. Aluminum 2.72, iron 7.2, gold 19.3, and honey 1.42, mercury is 13.6. All these sinks in water. Making a lactometer. For this we need a boiling tube, empty, refill with metal tip, pure milk, water, and both. First of all, this boiling tube is filled with pure milk, and we have to keep a empty ballpoint refill like this, and the metal tip should be downwards, and this ballpoint pen should not touch the walls of the boiling tube. The refill will not completely sink in milk, and we have to mark on the refill to which it is sink in the milk. We have to take out the milk and we have to fill with water and we have to keep the refill again. Again, it will not sink completely. We have to make a mark again on the refill so that it shows up to which it is sink in the water. Now, take out the water from the boiling tube and combine milk and water. That liquid, which is the combination of both, that is milk and water, should be taken into the boiling tube and we have to keep the refill again and we have to mark up to which it is sink in this liquid. You observe that the mark in the third case is in between the mark in these two cases, that is pure milk and water. By this we can verify the purity of milk and we can prepare hydrometer which is used to find out the density of any liquid. Here we are finding the effective density when two different liquids are mixed. The two conditions here are when the liquids are taken with same mass and other is when the liquids are taken with same volume. Let us go to the first case. Here the basic formula for density is mass per volume. Here the effective density when two liquids are mixed is total mass by total volume. Here mass of water is mW and mass of milk is mm and volume of water is Vw and volume of milk is Vm and density of water is rho W and density of milk is rho M. So total mass is mass of water plus mass of milk by total volume. This is Vw plus Vm. But the condition is these are taken with same mass. Means mass of water is equals to mass of milk. For our convenience, let it be M. And you have the basic formula rho is equals to M by V. From here I can write volume is equals to M by rho, mass by density. So VW is equals to, means volume of water is equals to mass of water, here it is M by density of water. And similarly Vm, volume of milk is mass of milk, here both are same, by density of milk. I am substituting these two in this equation. I am going to get rho effective is equals to M plus M by M by density of water plus M by density of milk is equals to 2M. Let the M may be taken out, 1 by density of milk plus 1 by density of water implies density, I mean effective density is equals to this M gets cancelled and 2 by, here I am going to take LCM, rho M into rho W and this is rho W plus rho M. Effective density is equals to density of milk, density of water by density of milk plus density of water. This is the formula for effective density when the two liquids are mixed whose densities are different and their masses are same and their volumes also different. This is the other condition in which they are taken with same volume. Again, the effective density is equals to total mass by total volume. Total mass is mw plus mm by total volume. The volumes are same. So volume of water and volume of milk both are same. I am taking that as V. So it is V plus V. Since the given condition is volume of milk is equal to volume of water. So let it, for our convenience, take it as V, and you have density is equals to mass per volume. From here, mass can be written as density into volume is equals to mass of water is density of water into volume plus mass of milk is density of milk into volume by 2V. This V comes out and it is density of water plus density of milk by 2V. This V gets cancelled and rho effective density is equals to half of density of milk plus density of water. This is the formula to find out effective density when two liquids are mixed with different densities and different masses but with same volume. Upward force in a liquid. To know about the upward force in a liquid, we need to do a simple experiment. This is an empty plastic bottle which is closed with its cap. It should be kept tightly. Now place the bottle in the beaker. Now the bottle will float on the liquid. Try to push the bottle into the water. We feel some upward force. If the bottle is pushed further, then you feel more upward force or increase in the upward force. And this force is called buoyancy. And this force of buoyancy acting on unit area of surface of the object is called pressure. So pressure is equals to the upward force by area. Let us find out the formula for atmospheric pressure. All the objects on the earth are subject to constant atmospheric pressure, and the atmospheric pressure is equals to force of the atmosphere by surface area of earth. The ratio of force of the atmosphere to the surface area of earth, let it be F by A. Now this force can be F is equals to, we can write the force as weight by area, surface area of earth. This weight can be replaced with mass of atmosphere into acceleration due to gravity by surface area of earth. We can replace mass with density into volume as density is equals to mass by volume. So mass is density of atmosphere into volume of atmosphere, and here you have G by A, and this volume again surface area of earth into height of the atmosphere into G by surface area of earth implies atmospheric pressure P is equals to density into height of the atmosphere into acceleration due to gravity. Measuring the atmospheric pressure, this is the instrument used to measure atmospheric pressure, which is called barometer, and this barometer was invented by Torricelli using mercury. This is the glass tube in which mercury is there. Here is also mercury is present at normal atmospheric pressure. The mercury level in this glass tube is about 76 centimeters. The state of mercury is at rest. So net force is equals 0. Means the weight of this liquid column is equals to the force applied on this liquid column by this mercury due to atmospheric pressure. Means weight of the liquid column means mercury column is equals to the force applied by mercury in the bowl, means this mercury. This force is due to the atmospheric pressure. Now the weight of the liquid column is equal mass of mercury into G, which is equals to force applied by this mercury due to atmospheric pressure, which is equals to PA. Why? Because pressure is equals to atmospheric pressure is force per area. From this I can write force is equals to P into A. Here let us consider as the pressure as atmospheric pressure. This can be written as mass is equals to density into volume into G is equals to pressure into A. Again I can write rho into density into volume. Volume is cross sectional area of the tube, which is A, into the force is the weight is because of this 76 centimeters only. So this is H into G is equals to atmospheric pressure into area of the tube. This area gets cancelled, and the atmospheric pressure P is equals density into height of the mercury column into G, implies P is equals to the density of mercury is 13.6 into 10 cube kg per cubic meter into height here is 76 centimeters. If I convert into meters, it is 76 into 10 power minus 2 meter, and G, which is equals to 9.8 meter per second square. After calculation, you will get the atmospheric pressure P is equals to 1.01 into 10 power 5 Newton per square meters, and this Newton per square meter can also be called as Pascal. So the atmospheric pressure P is 1.01 into 10 power 5 pascals. Here this is because density of mercury is 13.6 gram per cc. So this can be written as 13.6 into gram per cc can be converted to kg per cubic meter as 13.6 into 10 cube kg per cubic meter. And second one is this is height h is equals to 76 centimeters. 76 centi means 10 power minus 2 meter, and you have G, value of G is 9.8 meter per second square. Why a small iron needle sinks in water, and why a big boat float on water? For floating a body on fluid, force of buoyancy plays an important role. Force of buoyancy is upward force or upthrust. It is already explained in this lesson. How to calculate the force of buoyancy? For this, consider this experiment. This is a stone which weighs 500 grams in air, and this is suspended with spring balance. This is overflow jar which is filled with water up to its beak, and this is the other jar which is used to collect the water displaced by the stone when it is immersed. Now the stone is immersed completely here. When the stone completely immersed, the upthrust, the force of buoyancy acts on the stone, and there will be loss in the weight of the stone. Actually, the stone will not lose any weight, but due to the upthrust or due to the force of buoyancy, the stone seems to be lost its weight. When the stone is immersed in water, it displaces some water, and that water is collected in this beaker, and we have to weigh water in the beaker. The loss in weight or apparent loss in weight is equals to weight of the displaced water. So weight of the body means actual weight of the body is equals to apparent weight of the body when it is immersed in water plus apparent loss in weight. This can be measured with weight of water displaced. The loss in weight is because of the buoyancy, and this buoyancy is equals to weight of the water displaced. If the displaced water is more, then the force of buoyancy is more. In these two cases, the displaced water in the case of ship is more. So the weight of the displaced water is more, so force of buoyancy is more. That's why the ships float on water. This beautiful observation was made by the Greek scientist Archimedes, and he has given a principle which is called Archimedes principle. The upward buoyant force that is exerted on a body immersed in a fluid, whether partially or fully submerged, is equals to the weight of the fluid that the body displaces. Pascal principle. This principle is given by the scientist Pascal, and it explains what happens when external pressure applied to enclosed liquid. When external pressure is applied to the enclosed body of fluid, is transmitted equally in all the directions throughout the fluid and the walls of the containing vessel. This is the U-shaped container in which a fluid is there, and this is a piston, and this is a other piston. A force F1 is applied on the piston, then the pressure will be P1 is equals to F1 by A1. By this statement of Pascal, this pressure transmitted equally in all the directions, and this U-shaped container has a big chamber whose area is A2, and this is small chamber on which the external force is applied. Its area is A1. When this pressure is transmitted here, as A2 is greater than A1, then the upward force here, which is F2, then the pressure in the chamber P2 will be F2 by A2, but these statements tells us that the applied pressure is equally distributed, so the applied pressure is also distributed here. Due to the applied pressure only, the piston moves up with pressure P2. So I can write here F1 by A1 is equals to F2 by A2. Then the upward force in this chamber is F2 is equals to A2 by A1 into F1. The area of this chamber is too large compared to the area of this chamber. then the upward force here is much larger compared to the force applied here. Means F2 is very large compared to F1. This principle is used in hydraulic jocks. By the application of small force F1, this huge car is lifted here using Pascal's principle. So the Pascal principle is used in the design of hydraulic jocks and lifts.